Take a system with any number of degrees of freedom, moving finitely in every coordinate, whose variables separate completely in the Hamilton-Jacobi treatment. The abbreviated action is then a sum of one function per coordinate. Each is an integral of that momentum, and each is many-valued. When the coordinate runs there and back over its finite range, the action increases by 2 pi times a certain quantity, and that defines one action variable per degree of freedom. Now make the same canonical transformation as for 1 degree of freedom, action variables and angle variables. The equations of motion say every action variable is constant, and every angle variable is its own frequency times the time plus a constant. A there and back of one coordinate raises only its own angle variable, and by 2 pi. So any one-valued function of the coordinates and momenta, written in canonical variables, is periodic in every angle variable with period 2 pi. Expand it as a multiple Fourier series and put in the angle variables as linear functions of time. The time dependence is then a sum of terms, each with a frequency built from integer multiples of the fundamental frequencies added together. These frequencies are in general incommensurable, so the sum is not a periodic function, and neither are the coordinates and momenta. The motion is not strictly periodic, either as a whole or in any single coordinate. Having passed through a given state, the system does not return to that state in any finite time, but in the course of a long enough time it passes arbitrarily close to it. A motion of this kind is called conditionally periodic. If several fundamental frequencies are commensurable, the motion is degenerate. If all of them are, it is completely degenerate. The motion is periodic and every path closes. Degeneracy also cuts down the number of independent action variables the energy depends on. Degeneracy also increases the number of one-valued integrals. Without it, only s of them are one-valued. The rest are differences of angle over frequency, which are not. With it, a combination of angles is fixed up to multiples of 2 pi, and its cosine is 1 more. The Coulomb field is the example. Its extra one-valued integral is the vector peculiar to that field, and Kepler motion separates in spherical and in parabolic coordinates alike. One last remark. With many degrees of freedom, every action variable is again an adiabatic invariant.